Guys, welcome back to another video. This video will talk about the n-based form to represent the Fibonacci sequence. This video is made by Voidy and it may be published elsewhere on the internet by his friend Simon. The Fibonacci sequence is a very famous array. It is generally known as f0 equals 1, f1 equals 1, and fn plus 2 equals fn plus 1 plus fn, assuming that n is a natural number. But not all of us know how to represent it in this way. Fn equals fn, which is a very good pronunciation thing. And to be serious, let's represent the element of the n of the array in an n-fashioned way. And if we do it seriously, after all the serious computations, we may get this thing. And not all of us know this thing, right? But in this video, we are gonna get this thing step by step from this. The idea behind this deduction seems pretty natural and simple. What if we can turn this into this, and these two equations are identical? That is, what if we can turn this into this? We can turn this into this. If fn plus 2 minus p times fn plus 1 equals q times fn plus 1 minus p times fn, then we can deduct this step by step. Fn plus 2 minus p times fn plus 1 will equal to q times fn plus 1 minus p times fn, and that will equal to q squared times fn minus p times fn minus 1. And we do this step by step. We do the same thing n plus 1 times. We will have q to the n plus 1's power times f1 minus p f0, which is 1 minus p. This particular transformation will be called fn elimination in the future. But let's see. So our idea behind that is to eliminate one of the three variables, because if we look at the first equation, we have three variables, and now we'll apply these two things to eliminate one of them. And that will make things simpler. After making things simpler, we'll do something else to eliminate another variable. Then after a few fancy steps, we'll get this thing, this final result. And let's just compute p and q, because this is quite a doable transformation, because the only elements appearing is fn plus 2, fn plus 1, and fn. And that is pretty doable. So let's compute p and q. Let's write this formula down and let's do a few transformations. We put it right here and we split this brackets or braces or whatever apart. We'll have fn plus 2 equals to p plus q times fn plus 1 minus pq times fn. And that is identical to fn plus 1 plus fn, because this and these will be identical to this, which is 1, and these will be identical to this, which is 1 as well. And we'll know that p plus q equals 1 and p times q equals -1. According to some very famous theorem, PQ are the two solutions of a quadratic equation, that is t squared minus t minus 1 is equal to 0. Now we can apply the quadratic formula to get p equal to 1 plus the square root of 5 over 2 and q equal to this thing, or we can just reverse that. But let's just assume p equals this and q equals this, because If we reverse that, that do nothing to the final result. Now according to this, and we have the definite P and Q values, we have Fn plus 2 minus P times Fn plus 1 is equivalent to Q to the n plus 1 power times 1 minus P. And we can happily replace n plus 1 with n. Now Fn plus 1 minus P times Fn is equivalent to Q to the nth power times 1 minus P. Now it's time to do the Fn elimination process again. Now let's do something to this equation first. Do some pre-processing. According to some fancy transformation, Fn plus 1 is equivalent to P times Fn plus Q to the nth power times 1 minus P. That is a pretty simple fancy transformation. Our idea is Fn plus 1 minus something about n plus 1 is equivalent to P times Fn minus something about n. If you don't get the point of doing this, please watch the previous part of the video again. That is because the motivation for doing that is still Fn elimination. Let's call something about n(un). That means Fn plus 1 minus un plus 1 is equivalent to P times Fn minus un, right? And that means Fn plus 1 minus un plus 1 is equivalent to P times Fn minus P times un. We move this thing to the right part. Now Fn plus 1 is equivalent to Pfn plus un plus 1 minus P times un. That is equivalent to P times Fn plus Q to the nth power times 1 minus P. That means these two parts are identical. So un plus 1 minus P times un is identical to Q to the nth power times 1 minus P. Now it's time to make a reasonable guess. We make this reasonable guess that un is k times Q to the nth power, because this makes sense. We have Q to the nth power on this side, and we want to make sense, so we put this on this side. Now let's solve for k. We replace the left part with the representation for un. And now let's do a few fancy things. We apply the un and we divide both sides by Q to the nth power. Now we have Q minus P times K equals to 1 minus P. And that is, we can do this. K is equivalent to 1 minus P over Q minus P. And we do the calculation based on the previous P and Q values. And we can get that K is equivalent to 5 minus the square root of 5 over 10. Now the recursion begins. Fn plus 1 minus un plus 1 is equivalent to P times Fn minus un, or P squared times Fn minus 1 minus un times n minus 1. Now let's do this. N plus 1 times, we have P to the n plus 1 power times F0 minus U0, which is 1 minus K. Now we move this thing onto the right, and now we have Fn plus 1 is equivalent to un plus 1 plus P to the n plus 1 power times 1 minus K. We replace n plus 1 with n. Fn is equivalent to un plus P to the nth power times 1 minus K. And that is equivalent because we apply the UN formula here, that is equivalent to k times q to the nth power plus p to the nth power times 1 minus k. We can apply the values of k, q, and p right here. K is 5 minus the square root of 5 over 10, and q is 1 minus the square root of 5 over 2. P is this. And we can do a few fancy algebra. That is, if we divide this upper part of the fraction and the down part of the fraction both by the square root of 5, we can have square root of 5 minus 1 over 2 square root of 5. We put this 1 over square root of 5 away, and we have the negative sign of this, so that makes for this part. The same reason we can have this part. So the final representation, the final formula for Fn in an n-fashioned way is here. So let's make a summary. Throughout this proof, there is one idea. Fn elimination, that is to reduce the amount of variables. And that is almost the key point. That is the key point in almost all of the questions involving variables. From solving equation, we all know that we are going to turn variables into constants. And that is the way we are going to do it. In the next video, we are going to find out a more general rule for recursive sequences like this, not just the Fibonacci sequence, but all of the Fibonacci styled sequence. We are gonna find out the general rule for that, and that is the formula for Fn. Thanks for watching. If you are watching this on YouTube, please leave a like and preferably subscribe for more contents and miscontents. And if you are not watching on YouTube, if it is available for you, please visit my YouTube channel, which is Voice Skeleton. And of course, if you are not watching this on YouTube, it may be a pity for you because on my channel there is some spoiled fast noodles. So subscribe please, and I'll make an advertisement. If WeChat is accessible in your region, please subscribe to Simon's WeChat public account, and if you are interested but don't know what is his WeChat account, please leave a comment so that you could let me know. And that's it for this video. Thanks for watching.